So welcome to the FAIR Digital Revolution session. Digitalization is fundamentally changing our world, enabling new forms of collaboration, enhanced connectivity between people and objects, and innovative approaches to managing data and information. This shift marks a new era for metrology, creating opportunities for groundbreaking concepts and services. At the same time, metrology plays a crucial role in ensuring trust and consistency in measurement results within the digital landscape. To support this evolution, digitally accessible references align with the FAIR principle, so we heard a lot about that today, findable, accessible, interoperable, and reusable, as well as standardized ontologies and machine-readable methodologies are essential. As new reference systems are developed, cross-disciplinary standards and collaboration with other international quality infrastructure bodies becomes essential. It will not be possible to cover this vast and complex landscape today in this session, so therefore we will focus only on the core of the digital transformation, the FAIR principles, which form the foundation for making data and metadata truly usable at the digital ages. So I will start with the introduction of the first speaker, so Dr. Barend Mons. Dr. Barend Mons is a Dutch molecular biologist and expert in FAIR data. Early in his career, he focused on malaria research, later transitioning to data stewardship and systems analytics. He is best known for pioneering the work in scholarly collaboration, including nano-publications and knowledge graph discovery. In 2012, he became a full professor in biosemantics at Leiden University Medical Center. He led the 2014 FAIR Data Conference, which initiated the FAIR and Go FAIR movements. In 2015, he chairs the high-level expert group on the European Open Science Cloud. From 2018 to 2023, he served as president of the Committee on Data on the International Science Council, which is better known as CODATA, and was Europe's representative on the US National Academy's Board on the Research Data. In 2023, he also became a professor at the Leiden Academic Center of Drug Research, and last year, Dr. Mons was named Fellow of the International Science Council and was knighted by the Dutch King in the Order of the Netherlands Lion upon his retirement, recognizing his global scientific contributions. He remains active as a keynote speaker and advisor on FAIR and open science, so I'm very pleased to welcome Dr. Barend Mons.
Thank you. That's quite a CV. I'm retired, so of course it's long. Now I hope you do not expect too much. But I at least try to wake up people after lunch by saying stop data sharing, while my whole life was on data sharing, starting with malaria when I worked a lot in Africa and the data could not be shared. And I will explain, of course, that it is not really what you may think if you see the title. And indeed, some people see me as the godfather of the FAIR principles. You know, in the video we heard a paper that was cited a lot. Well, we just passed 17,000 citations on the paper from 2016 onwards, some signed 10 per day. But we have a nice internal joke that minimally half the people that cite the paper clearly never read it. So, still, after all these years, 80% of data, at least in my field, are not reusable. And that's the final aim of FAIR, of course, reusable data. We have recently, after 10 years, had another Lawrence conference where we rebaptized FAIR as fully AI ready, although AI, as we heard, doesn't exist, it's just a hype, it's statistics, but okay, at least the data going into these models should be as fair, as reusable and machine actionable as possible. Two major problems that you see in fake FAIR or FAIR washing, both terms invented by Roche, a pharmaceutical company, is that people confuse FAIR with open. They say, it cannot be fair, my data cannot be open. Well, FAIR data is not necessarily open. It's accessible under well-defined conditions. Our patient data can obviously not be open, that's clear, but also that it's a new standard and that you don't need to be machine actionable to be fair. there is not such a thing, before I even start, as fair without being machine actionable. That's in the abstract of the paper. So we classify everyone who cites the paper and say, oh, I put a DOI on my PDF, now it's fair, as fake fair. That's just as an introduction. So, of course, I'm not saying that we should not reuse data. But the key of my explanation will be that we go from what we call data sharing, the classical data sharing, where 90% of people you talk about data sharing, they think I send my data physically to someone else and I lose control. And then I'll go back to my African sort of research roots. A lot of African data on epidemics is now in servers in the north, and the Africans cannot even access them anymore. So the president of the African Union said at that meeting in January last year, you want our data, come visit us. So the algorithms can visit the data, and in the end I will say something about LIFES, the Leiden Initiative for Fair and Equitable Science. Imagine also that you can make an algorithm on a smartphone, send it out by 5G or 4G, it visits the same stations, as we call them, as the same algorithm created in Harvard or Leiden, but you could do that as a farmer in Africa, and fully participate in this global system of data visiting. So that's what I will be talking about today. And, well, we need to go machine-assisted, as we heard several times this morning. The data are so large and everything, but what is the real reason also to go to data visiting? Well, we know the many V's, the variety, volume, velocity, there's a new V every week. But very importantly, if we only look in the life sciences, my own field, we estimate that so far we have made 10 to the 14th assertions about something being true, like a gene causing a disease. If you put that in machine-readable format altogether, as nano-publications, there is no machine today that can handle a graph, a knowledge graph of 10 to the 14 triples. And if I want to get a DOI for each of them and I have to pay $1 per DOI, it's not going to work. That's very clear, digital object identifier. So we need to work with the volume, that is one. But on the other hand, the data loss is enormous. You see here a graph from an old Nature paper, seeing the decline of links that still work if you click them from a scientific paper. So one of the 7 capital sins, you can read on that in LinkedIn, on my LinkedIn post, is that the silverbacks, like me, but many of them only reward you for papers in Science and Nature and Cell and so on, and not for data sharing or making your data reusable. So the data are not treated well. Oops, they were on the memory stick of my PhD student and he went back to China. No way. 80% of the data is not reusable. Meanwhile, we create so much new data. In my field, we double the data every 6 months. Imagine how that will go on. And the computer cannot deal with that anymore. So we cannot even store the data on hard disks anymore. And biology can teach us how to deal with that. My little finger here contains 8 billion cells, which could contain 1 copy of a genome of all people on the planet. In one little finger, including the readout system, by the way. That's 14 billion DVDs. Imagine the volume of that, okay? So we need to really go to a very new era of dealing with data. And then privacy. Usually people connect that to hospitals, patient data and so. But think about it. We have people around the world already working with LIFES. If you publish the location of the last rare plant by Naturalis in the Netherlands, you can be sure it's picked the same afternoon. Our Indian friends are working on tigers. They have the snapshot cameras. So the sort of data you share is very important or make reusable, because it's fine to ask a question, how many tigers are left in India? But if you give the geolocation, they'll be dead the same afternoon. Privacy of tigers? I don't know. So it's not only that. Same example, mussel banks in the Netherlands. You publish where, and there is a law that if you even publish the metadata, they can request to get the data, and the same afternoon they will be all fished empty. And in some cases, you don't want to know about the patient. That's a minor thing. So there is also complexity. Now I will spend a minute on that because it's very important. So normally I have in a long lecture, I have a whole animation of this slide. It's a very complicated idea. It's the way we discover knowledge. Very briefly, I'll try to do it so brief that I stay in my 20 minutes. If you look at the left side, and you start at the bottom, you have a very simple algorithm, 1, 0, 1, 0, 1, 0, a pattern. You need a certain computer or understanding to predict the next step. If you make more and more complex algorithms and more complex data, that's the x-axis, and you keep adding CPUs or units of understanding, if you want to call it like this in lay terms, the line goes straight up. And essentially there is no chaos if you go on, because if you have unlimited intelligence, you see the patterns everywhere. AI sees a lot of patterns that may not be wrong, but they don't mean anything to people. Somewhere at this percolation point, as we call it, well, I don't think that works very well, but the green dot, that's where we discover knowledge. If you stop adding understanding, our understanding for any more complexity goes asymptotically to 0. Now, I'm involved in a big project called the Human Immunome Project, and everything we do with overlaying all these data is in something that we would call chaos. We hardly see the patterns. They may be there, but what we are looking for is actionable knowledge. And imagine that if we now, for all of the sustainable development goals, we have to combine health data, climate data, chemistry, pollution, and if all of them contain some of the errors we heard about this morning, and you overlay them, and you get mistake over mistake over mistake, in the end you get total crap, which we usually see from many AI models, obviously. So AI models just parrot what they saw in massive amounts of text. And actually what we are working on now with lots of programmers around the world is to try and make literally a slider that allows you to go from solid to gas or chaos to order and say, where do we find this narrow window where we really discover new knowledge that we can actually activate as humans? So, from findable, accessible, interoperable, and reusable, we now also go to fully AI ready. AI is in the middle of this. And I summarize the FAIR principles or the goal and the way to do it as the machine knows what I mean. Everyone can understand that one. So everything you measure or you do or you assert must be a so-called fair digital object, a lone-standing, machine-actionable unit of information. And that is, you know, a little bit of background, of course, is needed. You have this concept or an idea, like cancer as an example here. Cancer doesn't exist. It is a concept. You have individual tumors that exist physically. Then you have many tokens, cancer, malignant neoplasms, Krebskrankheit in German, kanker in Dutch, whatever, and a lot of identifiers in ontologies. They all refer to the same concept. So as long as you use what we call a globally unique, persistent, and resolvable identifier for everything you talk about, a gene, a protein, a building, a person, then machines can resolve it to what we call the intended defined meaning, and it becomes machine actionable. Now, machines are stupid, we know that. You have to explain everything in detail, otherwise they make big mistakes and they don't correct themselves. So, we are now trying to make things machine actionable, but what machines cannot deal with very well, and humans can very well, is dealing with near sameness. If I say to you, I love the piano, nobody thinks I love the instrument, you know, hugging it or whatever. So we fill in a lot of blanks, and we have enough agreement to communicate efficiently. Machines are unable to do that. They are black and white, 1, 0. So, how do we create what we need? Hybrid intelligence, which is bots and all kinds of AI that assists us, but feeds back continuously whether it's doing the right thing and so on. One of the big mistakes that I tell, you know, computer scientists, and they call me the stupid biologist, but okay, you know, so you've tried to fill all these holes in this machine approach. That is not needed at all. What you need is what we call knowledge. I have no time to go into it. It is, we have 1 million knowledge in the life sciences about every gene, every disease, and so on. They have a free-floating knowledge graph, and you see genes moving closer to diseases and so on. And now we are even able, very soon, to make machines at least understand something like near sameness. Okay, this protein is not exactly the same. One was made by the mouse, one by a human, but they are identical at the chemical level up to the amino acids. So for all practical purposes, in this particular case, I will treat them as the same concept, which is not easy. So what can we do with AI? Everything an ML or an LLM puts out is a hallucination, because it has no idea what it's saying. Some hallucinations we project intelligence on, like we do on animals. Our dog waves the tail, and we think, oh, it loves me. And if the dog thinks anything, it's food, 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 you know? So we don't have any evidence that this is really intelligent. So how can we go beyond the glass ceiling that we see today in AI, ChatGPT-5 taking forever and so on, is you need to feed these things with fair data, so they understand, quote, what they get in, and you have to constrain them at the output, what we call conceptual models, in which you define, again in machine-readable format, that it is simply, let's say, impossible for a protein to make a protein complex with a building. So you can restrain the output to something that makes sense to humans, at least, you know, and get much better outputs. Now, just giving a final thing on the sort of underlying technology, I cannot go into any detail, is that if you go in the life science, my field, from 10 to the 14th associations that are out there, and you only look at, I always take the old example of malaria transmitted by mosquitoes, you find that hundreds of thousands of times on the web, and even more than 10,000 times in Medline, you know, in the official literature. You only need to store that cardinal assertion once with 10,000 provenance files, so you know who said it, when, where, if it's contested or not. And then you can go to 10 to the 6th knowledge, which are free-floating knowledge graphs, and now you can deal with the life sciences data on a laptop. Okay, so we need to do a lot of work to get data manageable, but again, if you now want to cross-disciplinary borders, which you'll need to do for every sustainable development goal, understanding data from another field where they use other ontologies, other thesauri, term systems, data models, it's a nightmare. That is the biggest challenge for the coming decades if we deal with the reuse of data. Just a few final examples, and then I'll stop so we have time for questions later. This is a model we quickly built from this huge knowledge graph of 2.5 billion triples that we have, with a company called Euritos, with the doctors, and we saw here sort of the progress in at the gene level and immunological level of the disease of COVID, from I feel a little dizzy to I don't feel anything anymore. And then what we can do is we took all the drugs that were tested at that time in panic for COVID, throw them in the model, and each of them had a score. You can see hydroxychloroquine there, which was a disaster, of course. It has only one connection to the whole model. And we could predict straight away that it was wrong. And I think there's today 2 people that still believe it's useful. I won't mention names because of the privacy, of course. So what we are waiting for is actually hybrid intelligence, that we work with the machine to discover patterns. Machines are much better in pattern recognition than we are. That is not intelligence. The fact that a machine wins from the world champion Go or chess means chess is a stupid rule-based game. And if you make the computer play every chess game ever possible, of course it wins from everyone because it just sees the pattern. And that's what we cannot do. Is that intelligence? Up to you. Let's discuss it at the poster break later on. I'll be here till the end of the day. So, what we do is we have these connections, for example, between tocilizumab here as a monoclonal being used for the COVID. We talk to the people from Roche that made it, to the doctors, and say, this makes sense. But the picture was generated by the machine. That is what we are up to. Now, to end, how do we do this? We have this new initiative that is spreading rapidly around the world, the Leiden Initiative for Fair and Equitable Science, where we have the goal to make data reusable across the world in an equitable way. In other words, African researchers should be able to do it, but you should also not be turned away if you're Roche because you have .com behind your name. And that's what happens today. If Roche knocks on our door at LUMC, bang, door's closed. That is not fair. So, in small letters. So we recognize experimental data, real-world data and established knowledge. Experimental data typically is generated with a hypothesis in mind, but a lot of the sort of data that I saw this morning, satellite, whatever, is probably not even generated with a research purpose in mind. It could still be used for research later. And we have established knowledge, like we have this knowledge graph of 4.5 billion triples in the life sciences. You should never mix them, because think about this sawtooth graph, the machine will generate 5 million hypotheses per second that are useless because we cannot deal with them. And we make all these data fair. We make fair digital twins. It's not enough to have a digital twin. You have a machine actionable digital twin. That is not true for all digital twins at all today, but obviously they need to be machine actionable to be useful and to be able to be exchanged between fields. And then our goal is to have equitable, privacy-preserving, consensual, legal and distributed reuse. And I still have a very good bottle of 𝐏𝐻𝐈𝐏𝐿 red wine for everyone, and it's out there for 8 years. It's good wine, so it's not spoiled yet. For anyone who can give me a question that cannot be answered by distributed analytics, for which you have to pump the data around. So far, I still have the bottle. So we are working on that, on a library to make existing systems interactive so that trains can go around the world, and we have already by now more than 480 fair implementation profiles of all kinds of communities with co-data. By the way, there will be a question about that later, I think, that we tell people, okay, for environmental sciences already, an S3 or whatever has made a very nice fair implementation profile in which they have made choices on all the things on the left-hand side. In the back of this, everything is machine readable, so machines can also deal with it. And so, do I have to make your data fair according to ENVI-FAIR or Elixir or the European Commission or the European Data Space? Fine. It will go on and do it. And one of the examples that I love is Clara. She is a bot. I'm not against AI, but Clara is asking all the time, is this the right abstract that I created from your data? And we just did a very interesting data set from one of my postdocs, my successor, all the virtual variants of high concern of COVID that will statistically come up in the coming year, a few billion, and then trying to determine which ones are actually dangerous because they escape the immune system. So all of these proteins don't exist, and the bot creates all these pictures and even a slider. You can go through the molecule and see exactly when, with certain mutations, a binding site for antibodies will disappear or whatever. And this bot was only fed with CSV files and a master thesis of the student who did the job. So it's amazing what bots can do, as long as they're specialized and they interact with the user all the time. So that's what I wanted to quickly throw on the table. Stop data sharing, start data visiting. And here's a number of references. The slides are available for everyone to read, that this is not just a stupid biologist talking, but it's real. So, thank you.
Thank you, Barend. I guess we have a lot to think about after all what you have said, and I'm happy to find that EA could be even more stupid than I. So, just now I would like to introduce the next speaker. So it will be Dr. Mark Allen, the director of the Strasbourg Astronomical Data Center. He has obtained his PhD in astrophysics from the Australian National University in 1998. After a postdoctoral position at the Space Telescope Science Institute, he joined the Observatoire de Strasbourg as a CNRS, the French National Scientific Research Center, researcher, and became Strasbourg Astronomical Data Center Director in 2015. His scientific interests are the use of infrastructures of advanced astronomy and also the astrophysical processes at the centers of the galaxies. He has served as the chair of the International Virtual Observatory Alliance, the EVOA, and leads the virtual observatory aspect of the 𝐒𝐫𝐿 collaboration. So I guess, Mark, please, and you will have some use of fair data in astronomy. Yeah, thank you.
Thank you, everybody. First, congratulations to BIPM on its 150th anniversary, and the work that you do is really fundamental to so many areas of science. Thank you very much for the invitation. I think my role here is to bring an example of a field which is sharing data a lot out of necessity, and I'd like to really highlight a few of the things that enable that to happen. In astronomy, we are kind of lucky in many different ways. One is that while space telescopes and observatories and missions are extremely expensive, in terms of scientific impact, the best thing you can do when you get that data is to give it away for free. And so we are lucky in astronomy with that kind of aspect. So I'm going to introduce just a little bit. I try to make things as visual as I can. So I want to start off with a picture of the sky, maybe one that you are not completely familiar with. This is an all-sky image of real data that we have in archives around the world. What you see there is different bands on the sky. H-alpha is an emission line of hydrogen, the far ultraviolet, the radio sky, the flux map of stars on the sky, amateur data provided by people in the public. And now we see how you can manipulate that data to visualize the whole sky at once, and then zooming in to data that you are interested in, with systems that allow you to access just the data you need. I mean, we're dealing with petabyte of data behind there, and we are zooming into what we need. This is a particular galaxy. Its name is M51, and we can observe it also in detail in different bands. We can access the data, bring it together, and do different sorts of things with it. So that's just a quick tour of the sort of data that we have in the different archives around the world, provided by different telescopes and different data centers. So that's going to finish in just a moment. That's from the Hubble Space Telescope. Some data is spread across the whole sky because it's a survey, and some of it is pointed observations where you've directed the space telescope to, image that tiny part of the sky. Okay, so it's my obligation as an astronomer to show you beautiful pictures. So there's the first one of them. So just a little bit also about where I'm coming from. In France, in Strasbourg, we run a data center called the CDS. It's the Strasbourg Astronomical Data Center, and it celebrated a 50th anniversary in 2022. And we have a mission which is to collect data, to improve them, to put metadata on them, to distribute the results to the international community. We are a French research infrastructure, but our mission is to provide the data to the international community. And we can only do that if we really have active researchers involved. So we also conduct research on the data. It's science-driven. We are called a data center, but we are not just a building with some computers in it. We're actually data center in the sense of a scientific data center for reference data. And here's our picture. If we think of our CDS as part of the global data infrastructure, we are sitting there, well, we are active there in a community which is not all that big. There's maybe 30, 40,000 astronomers in the world, and they really are distributed all over the world. We are serving alongside of the big telescope infrastructures like those of the European Space Agency or NASA, the French Space Agency, CNES, the Japanese Space Agency, the ground-based telescopes like the SKA and the European Southern Observatory. So they provide data and they have their own clean archives. There are other data centers in astronomy as well, provided by NASA. There is a framework of sharing data called Virtual Observatory that I'll talk a lot about in this presentation. The CDS in Strasbourg, we have this strong link to the publications in astronomy, the major journals in astronomy. We process post-publication the data that is associated with a given paper, and that's kind of what we're famous for at the CDS. And just to give you a flavor of other things that are important in a data center that serves a community, we are certified by the Core Trust Seal, and we're involved in some of the networks that were just mentioned before, the European Open Science Cloud, World Data System, the Research Data Alliance, and we participate in European projects. Something like that requires a construction. You don't just make it happen, it grows, it is built. So in the case of the CDS, it's been there since 1972. So there was a big revolution that happened around 1992, 1993 with the internet. Our services were available before then. We would send microfiche, we would send CDs, we would send data tapes, and of course all that changed with the internet, and a lot of the progress that's happened after that has been because of the internet, of course. The online availability of archives, of data. In our case, we had infrastructures or collaborations that built up that really helped the whole community bring us to where we are today. In astronomy, we are often thought of as a good example of sharing data. There are some really great aspects, and I'm going to show you some of the best bits. It's not the case for all aspects, and of course we have a lot to learn. There's AI in the mix now. There are knowledge graphs. There are many different aspects that astronomy is not really at the forefront of. So I'm going to show you the things that astronomy is at the forefront of. One of it is sharing data, and we've really needed to share data. Why is that? It's because if you're doing the science where you try to understand the physics of a star, of a galaxy, of a planet, or of the cosmos itself, of the early universe, you need to combine data that comes from different telescopes at different wavelengths with different resolutions, and you need those data to be compatible enough so that you can combine them together and do the science that you want. So very early on in astronomy in the 1980s, there was a format called FITS, the Flexible Image Transport System. That is still in use today, and it's really an important part of our ecosystem. We also have a precursor to the DOI. We have the bibliographic identifier, the BIB code. There's an example of one of them there. And fortunately, we have a global cooperation about this. There's a bibliographic data center in the United States, supported by NASA, called the Astrophysics Data System, and everybody in astronomy uses it. Based on those initial successes, in the early 2000s, the concept of virtual observatory emerged. And that is the idea that the data itself, like we just saw on the screen there, kind of forms a digital sky, and that you can observe that digital sky with a virtual observatory. That's where for better or worse, that's where the name virtual observatory came from. And it is a fairly open and inclusive framework in that if you have data and you apply certain standards to it, you can make it available to everybody, and then it is harvested in a global registry and a registry of registries so that it's findable. And in Europe, in France, we have had projects which have supported that. Since about 2016, 2018, of course, there's a lot more awareness of FAIR. Many people in astronomy say, you know, we were kind of FAIR before FAIR was, we were there before FAIR. I really like the concept of FAIR because it puts a word, it puts an acronym on this concept that everybody can understand. So people in astronomy now talk about FAIR, people in other fields talk about FAIR. It allows us in these sorts of environments to be talking about the same thing, that data being findable, accessible, interoperable, and reusable. It can have a slightly different concept in each different field, but at least it allows us to have this discussion that I think really promotes the open science. So what is this virtual observatory? One expression of it is that it's a multi-wavelength digital sky that can be searched and visualized in different kinds of ways. That's kind of what I showed you just a little bit before. And so how does that work in just a little bit more detail? Let me give you this visual example of another one of my favorite galaxies in the sky called the Antennae galaxy. It's called NGC 4039, and it's actually two galaxies smashing into one another 45 million light years away, providing a spectacular thing on the sky where stars are formed at a much higher rate than in normal galaxies. It's just a really spectacular train crash in the sky. And so I use it as an example of how we can find data, access it, interoperate with it, and reuse it. So I'm going to use one of the tools from the CDS. It's a visualizer called Leiden. It's a way you can visualize the sky. Anyone can use it. It's free, it's open, it's downloadable, it's open source. We might want to search for this galaxy called NGC 4039. So I type it in, and that name actually gets resolved to a coordinate in a way that this tool can access not just data from the CDS, but data that's in the virtual observatory registry. And in this part of the sky, the part of the sky that you see in this image right now, it lights up green where a certain data center has data in that area, and it's orange, where you don't. Right, so that's very findable because the astronomical coordinates are understood, because those the metadata describing those is available in a registry, and we can have this visual exploration of data on the sky. It's extremely useful. How does it work? It's based on standards. It's based on a standard indexing of the sky, not just with your right ascension and declination, which is the astronomical equivalent of longitude and latitude. We can do much better than that. We have an indexing on the sky in a hierarchical system that allows us to describe complex regions on the sky, and it knows, because the map of what data is available at a given data center is just a set of integers that represents this map on the sky, and we can very quickly say, yes, we have data, no, we have data. We don't even have to make a query. We can just know that from the beginning that there's data available there and not somewhere else. And so in terms of being accessible, great, you find the data, you click on it, you can download it in different formats for science visualization and some analysis. It's interoperable because you have access to not just one data center, but all of the ones that comply with the virtual observatory standards. So you can build up this multi-wavelength picture, and in fact multi-epoch, because time is another dimension in this whole game, and combine it with a tool like this so that you can start doing things. Of course, young people today, they don't just want to click on an application on your computer, but our young astronomers, they're very programmatically aware, they're very skilled in programming and in languages. This is a Jupyter notebook where you can programmatically access those services, combine them, make cutouts, do the types of analysis that you need to do when you're combining one telescope data with another one. So that's reusable in the sense that it goes well beyond the initial purpose of the collection of that data to then be combined in a sense like this. And here's another picture that we show of what we train students and postdocs on in the interoperability of those types of data with different tools produced by different authors around the world, and showing what is possible. So there's a lot of training for young people about how to use these tools. And then what makes it possible? It's the standards. So the one that, my favorite one, of course, is the one which allows this zooming in and zooming out and finding data on the sky. We call it the hierarchical progressive survey. And it's an interesting thing. It's dealing with data on the sky. You're splitting the sky up into different segments so that you can index it in a hierarchical way. And then my colleagues tell me I should never use this slide. I mean, what are you doing? You're showing people a map of numbers in a table, and I'm saying, well, hang on. I mean, for me, this really shows what it's about. I mean, it's an indexation of the sky in different orders, 20 orders of indexing the sky. You're sort of doubling the resolution each time you go, and you can do that about 29 times with astronomical data. And the power, in my point of view, is that you can use this system to describe a very large full sky data set, which might have a low resolution spatially, with exactly the same system that you can describe an image taken with the James Webb Space Telescope or with the Hubble Space Telescope that's at a completely different resolution. So the same system works for that, and you can see the number of pixels that you would have in an image of the sky, which is at the resolution of the Hubble Space Telescope that covered the whole sky. That's not possible, but That's the system behind. And the power is that it's agreed upon. Not easy, but agreed upon at the international level through the IVOA with a recommendation that specifies how you do this and with reference implementations. So the body behind that is called the IVOA. It's a international alliance that develops the fair data management or the fair data framework for astronomy to enable new science through the virtual observatory. And it's a global enterprise. It was created in about 2002, and the different major national virtual observatory projects participate in that. There are guidelines for participation. There's no formal funding. There's no formal funding for that. It requires in-kind contribution. It requires making it worth your while to participate in the data sharing of the whole discipline. There's no extra body behind that does that. It's actually done by the people who are going to implement it. I think that's really, really important. There is an organization with working groups, the similar type of structure. And we have an architecture that was there before FAIR. My timing. I've lost my timing. You have to tell me when there's 5 minutes to go. So we have an architecture which maps onto the FAIR principles. There's, and there are 3 levels of talking about this, that you want to find data, you want to get data, you want to use it, you want to share it. At a different level, we put the language specific to astronomy on that we have a registry, that we have data access protocols, that we have metadata, and that we have different types of query languages, data models, formats, and semantics. And then the 40 or so standards that have been developed in this way map on to different parts of that architecture and correspond to different parts of FAIR. There's a lot of work behind there. This is the participation in 20 years of IVOA meetings twice a year with about 100 to 150 people who get together, either in blue in person or in red virtually, to make this process work, which is very much like the W3C process. And it's used. It's used by some of the major infrastructures in astronomy. You can see a picture there of the ALMA millimeter telescope in Chile and its data archive interface. They're using exactly this system. There is the square kilometer array, which is in construction right now. The prototype data access gateway for that implements these services from the beginning. The European Space Agency and its ESA Sky interface is fully built on the virtual observatory, as is the archive interface of the European Southern Observatory. A couple more slides. Deeper analyses of FAIR have been done, of course. I've shown you a kind of cartoon. I've shown you a nice walkthrough of what it means to be FAIR. FAIR actually comes with many details, and we have actually done our analyses of them. There are references and links to it there. The architecture of the virtual observatory is FAIR by design. The most important part is interoperability for us. In fact, since 2002, the IVOA is the International Virtual Observatory Alliance, which has interoperability meetings. That's what we call the main meeting, and we call them interoperability standards. There is, however, some differences in approach of astronomy compared to other fields. For us, the focus is more on the process of moving metadata from one place to another through the architecture. And the reusability is not so much specified, it's more implemented by the community services, whether it be the one that I direct or the one in the United States, and the other big investments from those space missions and observatories. In detail, we can do analyses like, in terms of the reusability. Where are we with that? I mean, this analysis concluded that we are mainly reusable. There are details like the licensing is not actually in the specification. It's up to the individual provider. Some of the big challenges that we have right now is the scalability to large data. You know, the data center I run has about a petabyte of data. In 2 or 3 years, we will have 5 petabytes of data. The square kilometer array, which has come in 2030s, will generate 700 petabytes of data per year. That's crazy. But we have approaches to deal with that. Some of it's cold, some of it's hot storage. Other elements are the hierarchical approach that I've shown you today. The IVOA at the international level is working towards machine readability, not just of the data, but of the standards itself. Because at the moment you have to read a document, understand it, implement it. It'd be really great if those standards themselves were machine readable. We're in this situation where we are now, like in this audience here, talking in very interdisciplinary environment. And the newly emerging open science systems, whether they be what's being promoted by the Research Data Alliance or what's being trying to put in practice through the European Open Science Cloud, is that we are trying to make all of those things somehow compatible. And that's a challenge. How do you make sure that the specifics of a given domain are taken into account in the generic open science infrastructure? And another challenge is to maintain the international support for the sustainability of those systems. So my last slide, just summarizing. So astronomy, we're in good shape in terms of being able to share data because it's not private or financial or sensitive data. So that's, I think, promoted a lot of the progress in astronomy. We've done some innovations for visualizing on the sphere. If you work on the Earth, if you work on a planet, if you work on some other coordinate system which is spherical, it would be really great to hear from you because we have some things that we would like to share. The astronomy specifics really go a lot into how those standards work, and I'd like to emphasize that it's a continuous effort to maintain, evolve, renew the standards based on scientific reasons and to find the right connections that we now work in not just disciplinary interoperability, but interdisciplinary interoperability. And with that, thank you very much.
Okay, thank you very much, Dr. Allen. We will now move to the panel session, and I would like first to introduce Dr. Professor Cornelia Dens. She has been president of the PTB, the Physikalisch-Technische Bundesanstalt, since May 2022. There, she supports the development of modern metrology along the major technological challenges. She was director of the Institute of Applied Physics and a full professor at the University of Münster. She completed her doctorate in physics at the Technical University Darmstadt on optical neural networks. Her research focuses on nanophotonics, biophotonics, and information optics. And she is currently one of the members of the International Committee for Weight and Measures, CIPM, where she is chairing and heading the interdisciplinary forum, Metrology and Digitalization, that cover within 5 task groups all fields of digitalization, from the digital SI, over FAIR and data quality, digital certificates and semantics, up to sensor network and AI. So I'm very proud to let you the floor, Cornelia.
Yeah, ladies and gentlemen, haven't that been 2 great talks? Are you already FAIR enthusiasts? So maybe if you think of the other words on this session, which is FAIR digital revolution, you could think, aren't all revolutions fair? And for example, you think of the French Revolution, which said liberty, égalité, fraternité. Maybe this was very fair because it leads to democracy and freedom. Think of the metrology revolution. Maybe to say for all people, for all times is also fair. So in a way, you could say these revolutions are all fair. So what is about the digital revolution? And here it's now different, because if we talk about fair, as you heard by our 2 speakers, fair is something different here. Fairness for all matter of digitalization means really looking, for example, of the fairness of the digital transformation of our beloved SI. Looking at the digital transformation of quality of data and, for example, of ontologies and semantics. Looking at the fairness of digital services, and also looking, for example, of the, as we heard, the digital data that are needed for digital twins, for sensor networks, or, for example, for artificial intelligence. So fairness means a lot. We heard already. It means findable, accessible, interoperable, and reusable. So on a first glance, maybe you say, easy. My data on my repository, I can find them. I use them. They are also accessible, and I operate them, and I can reuse them. But that's not meant. And as we heard, it's not meant how we as humans interact with our data. It's about machines. And machines are really not forgettable. They are not friendly. So they want to have it clearly. And that's why it is so important to look at fair data to also make the machine understandable and machine actionable. And that's why we're here. We do these topics in our forum, Metrology and Digitalization, and want to discuss it here. And we want to discuss it, as you saw, with two experts we already heard about. Barend, who I could say he is a data expert, and also with CoData, he's a liaison of our forum, Metrology and Digitalization. Then Mark Allen, we see he's a really expert in long-time data and visual data. And then we have two other experts here I just want to tell you a little bit about. We have Peter Thompson here, who is the CEO of the National Physics Laboratory, which is UK's National Metrology Institute, for now 10 years. Beforehand, he has studied and was a scientist in molecular electronics, worked then later on in defense and science, and also telecommunication. So he has overseen a lot of different developments and growth in recent years that are along the grand challenges that are in UK, but also worldwide. From time, quantum, medical topics, advanced manufacturing, to production and industry services. And all these include digital questions, quality of digital data, and also digital quality infrastructure. So Peter, maybe you are the one that is a strategic expert of fair data. And also you have been awarded from the Institute of Physics in 2022 the Richard Glazeborough Medal, and recently have been a commander of the Order of the British Empire, so congratulations for that. And you're a fellow of many of the academies like Royal Academy of Engineering or your Royal Society of Chemistry. You say that you bring passion for diversity and inclusion and a focus on maximizing impact for end users, for the industry. So ideal conditions to think of the fair digital revolution. And the fourth one is Venu Goptal Ahanta. You maybe have seen him yesterday also on the stage. Let me tell that he has two PhDs, on the one hand in physics from Tata Institute of Fundamental Research in Mumbai, but also in electronics from Tokyo University. And he's the director of CSIR, the Indian National Physical Laboratory. So he's on the one hand a researcher on nanophotonics and a lot of activities in light matter interaction. And of course, optics itself include many aspects of data handling. But he's also a fellow of the Optical Society of America, Optica, the Indian National Society, and also a member of CIPM since 2022, and in the executive committee of the Asia Pacific Metrology Program. So he oversees also a lot of organizations dealing with data. And he's also the president of the Optical Society of India, member of board of LIGO, and also everywhere where digitalization is also important for institutions. And so maybe you're also an expert of combining research in institutions for the fair digital revolutions. So now I'd like to ask all these four people that are so experts in fair data to come up on the stage, and let's start the discussion. So since we heard from you, Barend and Mark, already a statement, maybe the other two, maybe you can say in a few words shortly, what is your favorite topic in fair data, fair accesses, or what is the topic you think is most important of it? Peter, do you want to start?
Okay, thank you. Well, what a fantastic couple of presentations, and before I came to this stage and before I came to the conference, I thought, well, I won't be able to compete with that. What I do need to think about, and what I'm passionate about, is trying to sell and communicate the importance of fair data. And so I set myself the challenge over the previous 36 hours of waiting for that spark, that moment during the presentations that I thought, and that's why fair data is so important. So I enjoyed the entirety of yesterday. Bill, your presentation was fantastic as ever, and all of the presentations today. But the spark actually happened during lunchtime. And not when I was eating my lunch, but actually in a different conference. I wandered off from the conference, went to the exhibits, found myself drawn to the African music and the African cuisine and the courtyard of UNESCO. And the sun was shining, the 𝐁𝐈𝐿𝐿𝐿 was in the distance, the United Nations flags were flying. And I just went for a wander around the courtyard and I came across this sign. And the sign said agroecology. Now, what is agroecology, I hear you say? Well, I'll tell you, because it said it on the sign. It's nothing more than a method of production that reconciles the growing of plants in a living environment, the soil, that must be nourished and respected. You can see where I'm going here. And depending on how it's cultivated, the land will or will not continue to play its role as a medium for life. And my challenge is communicating the importance of fair data to the ecosystem that we work in. The SMEs, the conformance assessment companies, all the value chain, everybody that we work with, because this has to be a whole systems approach. And if you think about soil that supports the things that we eat, the eco-diversity, the flowers, the plants that we enjoy, it requires care and attention, hard work, and perhaps nothing happens for a long while. You have to nurture it, remove the contaminants, treat it properly, prepare it well, understand it, and then perhaps it will produce what we need, what we want. It will be resilient to the wind and the rain. And it will give us greater confidence to produce more and produce better, and it will be reusable and it will last longer. And that's the way that I think about the importance of confidence in data. It helps us to make better decisions, to be more productive, to be more prosperous. Technologists and entrepreneurs need to exude confidence to attract investment. Regulators need confidence in data to pass those technologies through their safety cases. I could go on about R&D and how much R&D isn't picked up by industry because of the lack of publication of the fair data and how unproductive that is. In particular, I hear it from the life sciences companies. And I thought about the comments that were made right at the start of yesterday, which applies to metrology and confidence in data, that we can enable greater confidence to tackle global challenges. Just 3 of those UNESCO Sustainable Development Goals about promoting sustained, inclusive and sustainable economic growth, building resilient infrastructure, promoting inclusivity and industrialization, and ensuring healthy lives and promoting well-being. So the case is sold then, isn't it? Fair data. We should all be doing it. But if I go back to this analogy with the soil, I'm an amateur gardener. I've said all of that, but do I do all of that with the soil at home, or do I do some of it and hope that everything else works? Of course I do, because there are other pressures and demands on my time. And I think that's where we're at with fair data, with the NMI community. I think we're committed. I think we see the benefits, but often change requires a burning platform, not a burning opportunity. At the moment, it feels like a burning opportunity. So there's much more work to be done.
Thank you for this analogy. Now, Veno, what do you think from your experience? What is most important for fair digital data? In short?
I guess, a lot has been said. So I would have started off saying that, boasting about optics, we have microscope, we have telescope, we have heard about how much data is generated for these wide areas of science. But from digital revolution perspective, I guess we all need to look at the quality of the data, the authenticity of data, as well as the reliability of data, right? So it comes across all areas of science, not just science. In these present days, possibly we also have to look at the data, the news which are getting it. So this also should be covered at some point, right? So how do we get ensured quality, reliable, authentic data, right? So that's something which we should look at, and the areas may be different, but we should take data as a holistic data and look at these aspects.
So maybe to the two experts, exactly the question. So is fair, other letters enough, or do we need to add matrix, quality, harmonization? And you said AI is also in fair, so maybe we need more letters in order to get more quality and harmonization, or is it all in the word fair already included? Maybe you start and then Mark.
Well, you hit a nerve here, of course, because I don't know how many people have said, oh, we need an extra letter to fair, and I'm totally against it. Of course, it would spoil the acronym, first of all. But secondly, that's not what they're meant for. The FAIR principles are just to make data machine actionable. You can make total crap data machine actionable. Yeah? So FAIR deliberately doesn't say anything explicitly about, for example, data quality. But I always say when people say, oh, quality, we should have a queue. I said, wait a minute. Data can be of low quality, low resolution, step counters, low quality data. Very useful if I have 1 million of them. So provenance is more important than quality per se. Because you can have relatively low resolution or low quality data, but the provenance is very clear. So I can, A, exclude them from my analysis if I don't believe them, but I know where they came from. And that's why this bot that I showed Clara, she asks you about your whole workflow. And you look at the R principles, because people say, oh, it's just the 3. No, there are many principles, and Mark already said you have F1, F2, you know, and it is the metadata and the provenance should be rich enough to make the data reusable. And if the quality is too low, given the provenance, they're not reusable. At least I won't reuse them. And you can determine also machines whether the data are fit for purpose. So fit for purpose implicitly includes quality, of course. I don't want to use crap data. But I am totally against extending the FAIR principles. We have other principles like CARE, and you know, that say, okay, this is how you handle data. Well, that's a totally different matter. So FAIR is really about making data machine actionable. Nothing else.
Yes, so Mark, your attitude with FAIR and other letters.
Well, I like FAIR a lot, but in astronomy we have lots of acronyms. And I've put a big, well, we have put a big effort into explaining FAIR to the astronomical community, and they also see that it's being discussed in other scientific fields. And like I said in the talk, I think the concept, the principles of FAIR are really resonating either with things that we're already doing or things that we can recognize we need to do in order to make our science more open or more fair. So already that goes a long way, and I guess my favorite part of FAIR is the sort of innovation that happens around it. You know, when you give people the opportunity to do things that allow data to be combined, you really are facilitating new types of science. But just quickly on the topic of quality, because the Virtual Observatory Alliance has been there for more than 20 years now, and it has some experience of the sorts of positive discussions you can have and maybe some of the negative ones you can have. And data quality was something which was extremely controversial at the beginning of the Virtual Observatory. People would say, you need to put this quality flag on this data, otherwise I won't know if I can really use it or not. And the counter-argument to that is, well, if you're talking about reusability, it's for a wide range of different topics, and data that may be good for one thing may not be good for something else. So you put the metadata on that allows you to describe that data well enough. And that's what we've sort of converged on. There is no kind of quality flag in the Virtual Observatory, but there's metadata description so that you, as a scientist, for your particular research, can understand if that data is going to be of sufficient quality to do what you want to do with it or not. So the data police shouldn't be there, but the metadata police perhaps should be, because we should describe our data in well enough. Well, I really believe in carrots rather than sticks, so I'm actually sorry I said that word police now.
So maybe it's also both. Metadata need to be fair and data either. I wonder, in your case, it's a long time endeavor. When you showed us in the beginning all the different images, they were from a long time. And then when you start, maybe 20, 30 years ago, there was another time of how to handle data. So did you start with ontologies already, or with semantics and architectures, or did they develop dynamically, and how did you ensure that from this long time data are always there to be used and to be helpful?
Well, in astronomy, there's a huge value associated with historical data, because you might have a star that goes supernova, you might have something that happens in time domain astronomy, and you want to know what was there before. So there's a huge value in keeping the data from, especially from publications. I mean, we would never think that a publication might disappear, right? You know, the major journals of our disciplines, we expect that they're going to be there in 50 and 100 years. And there is a concept in astronomy that the data, the reference data associated with those should also be there. I think that the ontologies and things like that, they started being formalized with the virtual observatory when we realized that we had to share the common descriptions. Otherwise, you know, radio astronomy would have built something and optical astronomy would have built something else. So I think the metadata was, the concept of consistent, uniform metadata has been in there for a long time, and sort of 20 years ago was when we formalized the virtual observatory. But the concept of data longevity and preservation is really important in astronomy, because it's central to what you are doing as a field.
So there we have maybe the for all times from metrology. Now, Barend, if you think of your activities in CODATA and FAIR, one endeavor is to share this data, or have the principle between different countries, between different regions, but maybe between different stakeholders too, scientists, industry and all. So is it for all people fair, or is there some hurdles still there?
Well, maybe it's good to say that actually I'm on holiday, so I only came from the campsite to give this talk, but I used the evening yesterday to meet in Paris with Simon Hodson, the executive director of CODATA. You know, I was the past president. Great time. And I think their role is crucial here. They have run this World Fair project. Some of you have probably been participating. And we collectively and discussed a lot about it yesterday night, defined the concept of recognized expert communities. Now, you're clearly one of them for astronomy, for example. And we want to mobilize those via CODATA. A lot of the unions are member and so on, ISC behind it. Because I showed this one slide with FAIR Connect, where we have already more than 480 FAIR implementation profiles. Now, let me say one thing. We always say for machines it's more important to tell exactly which choices you made for ontologies or conceptual models or thesauri and whatever, than exactly what you chose. Sometimes there is many ways to refer to a species or to geolocation, as long as the machine knows exactly what you mean. We approve them all. So what CODATA is uniquely positioned to do is to come up with a number of approved and recommended FAIR implementation profiles, as we call them, that list all these choices. And now, talking carrots and sticks, with the European data spaces coming up, for example, if you look at the regulation of the European health data space, which is ahead of the others, there's FAIR 3 times, in the right meaning, in our meaning, and it's all about reusability all over the place. So even a small hospital in the Netherlands will now budget $1 million to get compliant with the 𝐒𝐲s in 2027. That's a stick in a way, but it works much better with risk-adverse bureaucrats to say the risk of not acting. If you're not compliant, you're in trouble. Now they run to FAIR. So that is a stick. So what we want is to define recognized expert communities in many fields. They make all the choices, multiple choices maybe. In the United States, you will map your genes to NCBI, as long as it still exists, and in Europe to EBI, of course. But both is fine. The machine knows what you mean. So we want to recommend that, and then the bots, like Clara that I showed, will just ask you, you want to be compliant with Elixir or NVFAIR or the observatory, use this FAIR implementation profile. I'll make your data FAIR for you. It goes fully automatedly now. Unbelievable stuff. And that is the way to drive convergence. And I used to call that, I'm Dutch, so too direct in many cases, and Simon holds me back all the time. I called it convergence by laziness and ignorance, but that is now forbidden. So we now call it convergence by convenience. So a medical doctor uploads a CSV file, has never heard of RDF or ontologies or anything, and the bot says, do you want to be compliant with the European Health Data Space? Yes, of course. Okay, go. All the choices have been made. That's the role of CoData.
Yeah. So it seems to work for the medical area. So Peter, if you think of other industries or small and medium-sized companies, will they be able to have this carrot and take it over? Do we need to convince them how to go, for example, for digital certificates, digital calibration certificates, and make them fair? Or is it as easy as Barend said, just gives a carrot and everybody does it?
Well, I think the short answer is if we're to if this is to be successful, then the whole system has to come together. And if we're to utilize, if we're to exploit fair data, then traceable, machine-readable data that can flow through supply chains, flow through global supply chains. I'd like to think I'm an optimist, we'll still have global supply chains in a few years' time. It will increase interoperability, real-time verification, automated compliance, but you have to sell the benefits to organizations that perhaps aren't as data and technically literate and have far fewer people and far less time to invest in something that perhaps you're selling a benefit that will be in the future. So obviously regulation is a stick, and in highly regulated sectors, then that would be easier. But in the sectors where we're innovating, where we're developing new technologies at a rapid pace, then yes, those inventors, those SMEs, those micro companies, this is going to be a challenge. We've got to sell that message and sell the benefits if we're going to achieve this.
Maybe I can add, when we think of distributing our digital calibration certificates with fair data behind, then for small and medium-sized companies, the status now is that if they have a PDF calibration certificate, they have to type in things from that to their industrial processes. So having it machine actionable means no errors, being more efficient, being quicker, and maybe this is not a carrot, but it's an incentive to do so. But maybe
one small addition there. My experience over the last 3 years is industry is getting ahead of academia in fair. The term fake fair and fair washing comes from Roche. You know, they hire companies to make their data fair, they go flat on their face, they say they can do it. That's why they join LIFES. They say, we want qualified providers. So industry, especially the pharma, but I see agriculture everywhere, they're moving ahead. Exactly as in the beginning of the internet. You know, George Strawn is one of our big advisors. He handed over right in time to industry and TCP/IP in the center of the hourglass, and the rest is history. We're approaching that point for the Internet of Fair Data and Services already. So industry is actually taking over.
That sounds great. Maybe, Vino, if you go to more other things like sensor networks or AI, what is the role of FAIR there, for example, for science or for metrology?
Right. I mean, I guess at a layman level, like, so if you see the science and the AI, they're seen as two sides of a coin, right? In the sense that, like, the science is science-driven. You have some models which conform to the data conforms to it. On the other hand, AI models, they're built purely on data, right? But there is a handshake between them that, like, the data has to be qualified by making it compliant to the model, a science-based model, right? So that way, like, yes, I mean, to have quality data, I mean, I respectfully disagree with you because I'm scared about my health if low-quality medical image, like, no, I cannot accept it, right? So, but for astronomy, possibly, like, as large number of images could help reconstruct certain area of the space, that's okay, right? So, yeah, so basically what we have to look for is and data where we have reliable data, high quality data. For that, like the sensor networks is one thing which we need to integrate and collect large amount of data and then develop models, right? For industry, again, that's a challenge because the parameters vary from industry to industry. So where do we start? Where are the models? Like, so which model or which industry we start with? So that's something which probably we need to be worrying about. And then I completely agree with you that like the industry is going forward, and unless we act fast, like so, we'll be laggards.
Maybe for AI quality assessment, there might be a new role of data, because you can use data to assess the quality, like in black box models where you send in data and you see the results. And if your data have been quality fair like before, you can check if the results are right.
Yeah,
so
but if you let AI do that, you have the big chicken and egg problem, of course. We know that. And of course, I'm not advocating for low quality data. Huh? But how do you determine what is low quality? As Mark said, for what purpose? You know, and if it is all about my life and death, and not what happens in a billion years from now, we probably have a bit more quality issues there. But again, provenance is needed to determine quality. Otherwise, there's no way. Who says this is high quality data? Even that's provenance.
So before we discuss a little bit what will be in 10 years and what will be metrology about, maybe we open this to the public and I ask you to ask questions. I already see one hand rising. I just go over here. This microphone, so Frank Hartwig has a question. Where's my microphone here? Can you switch it on? So, Frank Hartwig, please. Maybe you get a microphone soon from somebody. Yeah, it's coming. Maybe if others have questions, they can already raise their hands, and then I can see if there are others having questions. Yes, I see you. Thank you. Okay.
Yeah, Frank Hartwig from PDB. So we are celebrating 150 years CIPM. And before this situation, we have had the chaos with different physical artifacts, lengths, kilogram, and so far. And it was one success that we agreed to have this international kilogram prototype, meter, and so far. If we look today in the field of digitalization, we see thousands of different standards. Finally, in my opinion, we are pushed back to the Middle Ages in the field of digitalization. And now my question goes to Barend. Do you see any chance that we have in future, let's say, a universal format, that we speak only of one format? One important point I forgot to mention is that all decisions in the internet or in AI are based on data. But data are worthless, that we all know in the room, if we do not have the units. And so my question is, do we have the chance to have one common format in the future, or is it more going in the way that we can translate from one of the established formats to the other ones?
Well, there's of course two sides to that coin as well, because first of all, why do we still have inches and centimeters? You know, we have not normalized everything even now. What is so important, and coming back to this example of CODATA, one of the participants in the World Fair project was the group that created DRUM, Digital Representation of Units of Measure. So we consider that most of the data that we see in the world across disciplines can be formatted using about 130 semantic types. Some of them are very generic, like units of measure. If you don't use units of measure, what are you measuring? Geolocation, people, organizations. If you go down to cell types and cells, you're a life scientist most likely. So these bots that I showed, I couldn't show them live, but I can show them later to you if you want. They actually recognize what your profile, your semantic profile is. And one of the things that CODATA would recommend now is if you have a column somewhere and it's centimeters versus inches or molar versus concentration, the unique identifier to determine the units of measure should be there. And then the machine will easily turn centimeters into inches, and we don't lose the second Mars lander, you know, that NASA thought that 𝐸SA would also measure in inches. So that is, I think, the way forward. We cannot force the world to all drive on the left or to all use exactly the same thing. But if machines know which units of measure are used, and they use drum, so we will recognize this very clearly and ask everyone to make absolutely clear to machines, and therefore also to people, what units of measure were used and resulting in these numbers. So that's the only way forward, I think.
Yeah, so the BIPM has also now the digital representation of the SI, so the SI digital reference point. Hopefully it's the same as a drum.
Yeah.
So you would say on another sentence that instead of having in the Tower of Babel only one language, you have a lot of translation of languages, so many languages can understand each other by translation.
Yes, I mean, now that you say it, we had a lady working with us in TNO, and then she went to the Ministry of Health, I won't mention names, and she said, now I want to really understand FAIR because I go to the ministry. And I took a whole morning to explain all the details of FAIR, but she is not very technical. So she said, I think I got it in the end. She said, you have Google Translate for data. I said, now I can either jump out of the window because I wasted a whole morning, or this is maybe the way you present it in the ministry, because in the end, it's what it is. Of course, there is a whole world below Google Translate and what it is today and what it was 10 years ago. But indeed, you can never force people to use exactly the same units of measure, all these things. But as long as the machine knows what you mean, there we go again, the machine will easily translate stuff. As long as we have, for example, 3 models, 𝐻𝐿, OMOP, and FIRE in health alone. The hospitals use FIRE, the industry uses OMOP. But the machine can, Clara will ask you, do you want your data in OMOP format or FIRE or both? Fine. Who cares, you know? And a visiting algorithm saying, I have a FIRE question, oh, my data are in OMOP, we are working on a library to translate the question into OMOP identifiers and you get the right answer. So the worst mistake we have ever made all over in history is we have too many standards, let's make a new one. So let's not do that.
And then Peter take over the advertisement in a well way. I think there was a question here. Yeah, raise your hand again. Yeah, can you get a microphone? Let's see. There it is. Yeah, thank you. And then it's your bill.
Thank you very much. I'm Marco Scharke, also from PTB, and I'm a scientist in optics and a big fan of FAIR principle. And I would like to make a remark and ask a question about FAIR, like on the basic of the individual implementation, especially like in scientific publications. So FAIR is great, and scientists tend to be very cooperative, but of course there's also competition, and there are strong restraints on time. And sometimes I have a feeling like if you do the FAIR, it's not super rewarding. So because if you save the time, you can do something else. And my question would be, what can be done, like as community or at an institutional level, to make the FAIR principle for the individual more rewarding, or maybe even to make it mandatory instead of optional, to be more fair.
So Peter wants to answer on that?
I'll give a perspective from an NMI before perhaps more eminent scientists than I might comment, which is literally in the last week we submitted a paper in which we submitted all of the data in FAIR format, and one of the reviewers used that data to run the process themselves, to assure themselves, and in fact that paper is now going to be published in Nature Comms. Now it may have been published anyway, but what I'm doing today by saying this out loud is what we need to do when these things happen, which is to make it clear that that may well have been a contributing factor as to why that paper was published. But I'll leave it to our academics who may have different perspectives.
I'll be very short because I'm talking too much. So you want to comment first? Because I will just refer to my LinkedIn posts.
Maybe Mark, I think the question was a little bit also to you. Yeah.
In terms of encouraging authors to make their data fair, I think we do need to reward it. I mean, we should, in the evaluation of researchers, in France there is an effort towards doing this. It's slow, but I think it should be part of the evaluation of researchers about whether they have contributed to, the fairization of their data. So that's, on one hand, the role of our academic bodies, whether it be the CNRS or university promotions committees, they should know about that sort of thing. On the other side, the moment when a researcher is finalizing a paper, because they want that to be accepted, that's the moment when they're paying most attention to all of the things about publishing that paper. And I think that should also be the moment that the emphasis is on, have you provided that data to either a certified repository? Have you complied with what the journal requires in terms of making that data available or described at whatever level? So I think it should be part of that publication, but it should also not be so onerous. It should not be too difficult. I think that there should be tools that help you. We run a data center which is connected with the publication process of some of the journals. And we know very well, because of the volume that we process and the amount of time that a researcher has to put on, you have to give tools put tools in the hands of researchers in order for that to all happen.
Yeah, thank you. I think most of the journals ask you now to give information where your data are, but you can still answer my data are on my repository and ask me if you can get them. So that's maybe
and it's impossible for funders to check. Because do you send a reviewer to an RDF file that is abacadabra? So now with this open data article, which is available to all publishers, the funders in the Netherlands already have told me, we will fund the APC, the article processing charge, for that open data article. Now we can prove that the output of our research is actually fair. But to answer the question of the gentleman there, not long, but go to LinkedIn, check my LinkedIn profile, and I published the 7 capital sins of open science. And the first one is Silverback's, only looking at age factor, and I deliberately mispronounce it as age, of course. So please go there and we can talk about it all the time. But you're very right, there is no incentive.
Bill, your question, can you give it to Bill Phillips here, the microphone, please? Or I can give it to you, maybe. Thank you, you're there, yeah.
So my question is for Mark Allen. Toward the end of your talk, you sort of teased us with the idea that you had something interesting to share about working on spheres. And I want you to say a little bit more about that. And the thing that motivates this question is, as an atomic physicist, I'm often thinking about two-level systems on a block sphere. Some people will know what that means. And I work in, when atoms have angular momentum as a good quantum number, I use spherical harmonics. And I might even be interested in how you develop a satellite navigation system on the moon, which is sort of a sphere. And so I want to know more about what you have to offer people who deal with spheres.
Well, I thank you very much for the question. I'm not sure it's of interest to everyone in the room. I just love this way of indexing the sphere. We can thank very much the 17th century mathematicians who came up with the partitioning of the sphere. We use what's called the hierarchical equal area projection on the sphere, 𝐿𝐴. And it was used a lot by the cosmic microwave background experiments, COBE, etc. And it was set up in a way that you could easily do Fourier transforms of isolatitude data on the sphere of the cosmic microwave background. Essentially, it's a way of indexing data on the sphere in a hierarchical way with equal area cells. And the systems we put in place, it's a bit like anything that you've got that's either data, like the value of a pixel, or some information that can connected to a region on a sphere. It's like a little box, it's a container. You can just put it in that box. And then when you've got a lot of data like that, you can very easily get to the data you want quickly. So that's why these systems that I showed you work. It's been applied to planetary surfaces, not just the celestial sphere, but to planetary surfaces and counting craters on the moon and things like that. We've applied it, well, we've had visits of the EU METSAT, the Meteorological Satellite Data Center, who are interested in how they use it for meteorological data. It has obviously applications for earth science and for other fields. I was trying to find people like you who are doing things on a sphere just because it's mathematically very fun and really interesting as an approach. So I'm very happy to talk to you later. And the basic thing that we offer is the 𝐿PICS and 𝐻IPS standards for manipulating data in this system.
Yeah, that sounds great. Thank you for the questions. Maybe other questions can be asked in the break. Maybe Martin, the director, maybe has the last question for it. Yeah. But anyhow, just in between, there's a lot of geodesy that is now done with optical clocks, and there the sphere of the Earth is measured, the geoid of the Earth is measured very precisely, which could be an application to your suggestion. Martin, please.
Thank you, Cornelia. So it's mandatory now in every talk to talk about AI. And that applies to all of us, I admit the same thing. And it seems also mandatory to express our own opinions on whether we like it or are optimistic. Cutting aside from all of that, we know that the performance of AI is critically dependent on training data, and in some systems there's search functions as well, but training data. So my question is about training data. Do we know enough about what we can do, should do, to make our data, and of course we all think our data is the best and should be indexed by AI, fully visible and efficiently readable by AI systems? I mean, you've got an enormous repository there. Do you have processes by which you work on the data minded to be preparing it to be read by AI? And I extend the same question to Barend. Do we know that if we set up, for instance, your systems of nolets and your very, very many number of triples, do we know that if we structure all our data very nicely like that, that it's going to be better, quicker, read, more visible to AI systems?
Our basic approach to that is to make the data easily accessible and well described. At the same time, absolutely terrified what might come of that, in that our data, we know very well it's being scraped all of the time. On one hand, if someone does something better with our data than we do, then okay, maybe that is okay. On the other hand, I think we are kind of the custodians of the scientifically validated data with integrity. And some elements of this were mentioned in the NIST talk this morning. You know, NIST has a role, even if there are, industrial interests that take things from you and then develop them further. You know, they have a different interest, and I think our interest as a sort of scientific body is to maintain the scientific integrity of the discipline. So I'm terrified what might come of some of the AI things saying, we got the data of astronomy, and by the way, now it means that, there's life on Mars, or there's, something outrageous, outrageous interpretation of the data. So I'm all for new techniques to use our data and to apply it in the scientific method. Terrified of it being used in non-scientific method, but at the base level of making the data interoperable, standards is for us the way we do it.
And maybe think of some positive thing. Looking for exoplanets all over the whole universe would be nice to have some machine as AI just taking some job from you, and then you can control it at the very end. But it's easier then from the vast data to see some of the exoplanets and then start over. There are plenty of projects around the world that are doing that. Yes.
So maybe one more issue there. It is not enough to have 4.5 billion triples if there is no conceptual model that constrains it. Machines don't have a conceptual model. I remember when I told a friend many years ago that we were freezing malaria parasites, unicellular organisms. He's a clever guy. He said, but then their heart stops beating. So he had no conceptual model of what a unicellular organism is. And machines don't have a conceptual model at all. So by nature, unless you feed it to them or they are trained, like we learn over time. So I think the data that go in need to answer to a proper conceptual model. So they don't have crap data in there. And the output is all hallucinations. As I said, machines have no idea. There's not a generative AI machine says, oh, I made a beautiful picture. Now the tears come down my eyes of the beauty of that picture. No, just pixels. But we project feelings on that picture. We love it, a poem, whatever. There's nothing there. So if we constrain as I said in that one slide, the output of AI to fit our conceptual model of the world, and from different disciplines looking in a different way at the same truth, then it can be useful. And that slider is my dream, because if you then move it to the right, you will get more chaos, but you get also more serendipity and more knowledge. While if you move it to the left, you get decision support in health. I don't want a doctor to try something out to me that some stupid machine came up with, of course, that's clear. So we need to be very careful how we constrain AI and see it as a stupid tool helping us that does the hard work. Pattern recognition, computers are much better, but that's all they do. And then they come up with some statistical output that looks very nice to us. And I hear more and more people even saying that the better these LLM models become, the more crap they spit out that you don't detect because it looks so logical. They told everyone now, I'm a co-founder of the gene ontology.
But it might not be a large language model. It might be other AI that is...
Any AI.
Yeah. Maybe
and it's traceable back to the data, because if we would have written go fair with the dash in between, it would not have happened. We found out. Because the machine doesn't know that's one concept, go fair. And gene ontology is the acronym for go, GO. I'm a geneticist, so it concludes I must be, because go is all the time statistically connected to my name, so I must be a co-founder of gene ontology. I always missed it in my own CV. That is total nonsense, because it looks very nice. That's the danger.
We could discuss for a long time, but we come to the end, and maybe everybody says in one sentence, in 10 years, with metrology and with fair data, is everything done? Machine can read it for all times, for all people, everything's there, but or are there challenges in 10 years? Peter, you want to start? One sentence.
One sentence, I've got 3 points. So I'll not use any punctuation. In 10 years or so, we won't be talking about a digital revolution because it will have happened. It will be, and all the great work that the BIPM, and I know Euromet are running a workshop on this soon, that will have permeated. That's not to say that there aren't huge challenges with legacy systems and training and development within NMIs. So that's my first point. My third point, I'll finish on AI. I won't break stride. My second point is around autonomous systems. We're going through a period of semi-autonomous systems, which in of itself is probably the most challenging. When we moved, for transport, for example, when we moved to fully autonomous systems, I think systems will be safer without the humans in the loop. In 10 years' time, I'd like to think that I still won't have been divorced by my wife, because I drive a semi-autonomous system and it regularly takes over control of the car when it believes I'm not doing something safe. And this provides my wife as passenger with a real-time feedback opportunity, which she regularly takes. And I thank her for the feedback every time. And then finally, because we have to talk about artificial intelligence, just applying those same metrological, that mindset, those approaches, the metrics for reliability, bias, and explainability. And as somebody suggested earlier, it's not a new thing. There was a news article written in the 1990s about MPL, actually, in which it referred to a workshop that MPL convened in 1957 to bring organisations together. It said at the time to discuss artificial intelligence. I'll give you the one sentence is the review of the workshop, if I might, which is the workshop was actually called let's have a look at the mechanisation of thought processes, and the person who reviewed it gave it this review. The symposium was generally considered to have been highly successful, even though inevitably a great deal of nonsense was talked by some participants.
So in 10 years, still some turn. So, Mark, with a shorter sentence, what will be in 10 years about fair data?
Okay. Not just machine-readable data, that I think we have a lot of now, but machine-readable standards so that those things can be constructed, whether it be by AI or others. And I would say a revolution in scientific publication that takes into account data publication.
Thank you. Venu.
Yeah, if everything works fine, we cross the barriers of semantics and we speak same language, which is machine readable as well. So then I hope so we'll go cross-operable systems where, as already mentioned, so we have wide scope of applications. So I think we should go to cross-industry operable language or models.
And last short word.
Yes, I will not compete for the longest sentence ever, but I think that sin number 6 in the list that I just mentioned is that everybody wants to fund rocket science and nobody wants to fund the rocket launcher. So unless we spend 5% of our research funding on the infrastructure needed to actually reuse the data, it will fail.
Thank you. So now you have a lot of things to think of, to think of digitalization, to think of a world where this happens for machines and for humans. And as humans, maybe now you deserve a tea break and discuss further with our guests and give them applause. Thank you very much, all you four, for this presentation.